Okay, so this is today's Leetcode Daily problem. It was actually pretty hard task. I didn't manage to come up with a solution, so I just look up the hints, and the hint is the problem is this, so like I need to find the smallest integer that consists of all ones that's divisible by k. The problem with the solution is that the k can be quite large, and the n can be like the length of these ones can be like so huge that it even like Python would be able to handle that number of values, and it cannot like hold it in one integer or like in one number. So let's say you have, as they say, and when it's not possible, I should return basically -1. So let's say here k is equal to 3. So I need to find the smallest number in the form of 1, 1, 1, 1, 1, 1, 1, 1, 1 that consists of only ones, and this is length should be minimal that, and that's gonna be num so that the following holds: num mod k is equal to 0. So there, if I start and this and I should basically return this length of this number result. So the problem is, as I said again, this number can be so huge that it won't fit in a memory, or like won't fit in a number, even for Python. And I need to, every time I increment this number by 1, or like, let's say I check 1, and then, okay, I do 1 mod k, check if it's equals 0, and then I check 11, and I check 11 mod k, and if it's equals 0. And then if not, I should check 3 ones, 111, and check if 111 mod k is equal to 0, and I should repeat it, so on and so forth. And the problem there is that I can do that forever, yeah, and like increase this one, like add another ones to the end, and like check the mod, check the mod k, and if it's like equal to 0. So first of all, I need to painlessly, or like to add additional 1 to the number without like sacrificing this accuracy, and like without holding this in a single digit, holding this number holding this value in a number variable. And so first hold 1, 1, 1, 1 in memory, or equivalent of that. And second of all, I need to check 1 1 1 1 1 1 1 mod k, efficiently. And third, I need to figure out when to stop, so that solution does not exist. So there should be like this 3 conditions that are satisfied in order to solve this problem given the constraints that were given for this problem. So and based on this, there is a clever trick how it can be done. So let's say you know that 1 mod k gonna be equals, let's say, s. So having and like it's not equal 0 there. If it's equal to 0, then return immediately like n equals 1. If it's not equal to 0, how I can, knowing this value and something else, how I can figure out what's gonna be next number. So I just adding 1 to the end of 1. How to figure out what's gonna be 11 mod k. And there is a clever trick how to do that. So 11 mod k can be written as 1 multiplied by 10 plus 1 mod k. And this one can be written as 1 mod k multiplied by 10 mod k plus 1 mod k, and then the entire expression is mod k. So this one is equal. And what do we know from a previous iteration? We definitely know this part because we defined it here. So it's equal as. And then we can calculate always this as a constant. And this is also the constant. We know that. So that if I do 11, let's say 111 mod k, it's gonna be just 11 mod k multiplied by 10 mod k plus 1 mod k, and then entire expression mod k. And I figure out this value from the previous one. So if I found here, and I can even like substitute this expression into here. So like it's a recurrent recurrent expression, and then I can like just linearly move from one expression to another by saving the previous one, by saving the previous value. So the formula gonna be let's say mod k, let's say mod k n minus 1 multiplied by 10 mod k plus 1 mod k, and then entire expression mod k, and this is equals mod n k. So let me write it more clearly. So mod n k equals minus 1k multiplied by 10 mod k plus 1 mod k, and then the entire expression is mod k. So that's gonna be it, and let's check what conditions were satisfied. So I can hold 111 or value in a variable or equivalent of it. Yes, I can just hold mod n minus 1k to calculate mod k, mod n k. This is like store mod k efficiently, just one variable, and again, like having this recurrent formula helped me a lot. But how I can like figure out when to stop, like when the solution doesn't exist. So let's say I have mod k, let's say mod k kn is equal, let's say s1, and then mod n plus 1 k is equal s2, and this is not equal 0, and this is not equal 0, and let's say some mod n plus m k is equal sm, and this is not equal 0, and not equal sm, but equal s1 actually, and this is not equal 0, and it means there is a cycle when and if there is like repeating values in a recurrence formula, it's gonna be a cycle, and I'm never gonna reach the 0 in this case, because I start over again and then gonna go again with the cycle and then with the cycle, and then it's never gonna be 0 no matter how long the n is. So in this case, as soon as I figure out, okay, there is a repeating value of mod n k, so I have the set that can have up to 9 values, not 9 values, but assume k minus 1 values, k minus 1 values maximum, and if those values repeat, meaning let's say I found the value that current mod nk value is in this set, it means that I'll start over like applying this recurrence formula, and like it will start over like having the same set of values, and it seems, and it means that it's cycle, and it means that I need to return minus 1. So like all these 3 conditions are met now. This one, hold in a variable, or hold 101 in a variable equivalent, efficiently calculate mod k, and then figure out when there is a cycle. So I'll start solving. So I have set s equals set, and then while let's say res equal k, and then counter like mod n k equals 1 mod k, and then counter equals 1, and then while mod n k not equal 0, I'll do modern k, let's say a set add mod and k, and then here mod and k equals mod and k mod k multiplied by 10 mod k plus 1 mod k, and then everything mod k, and then if mod and k contains if set contains mod and k, then return -1, otherwise I'm gonna go set add again, set add, and then counter plus equal 1, and then return counter, something like this. S in mod and k. Oh, vice versa. Mod and k is in S. Yeah, so that's gonna be it. It seems like there is even more efficient solution with so it turns out I can avoid using the set and just use the mod 2 and mod 5. So if k mod 2 or mod 5 equals 0, return -1. Can I do this? Yeah, that's very interesting. Why is it so? Do we have editorial? Checking loop. Yeah, it seems they don't know about this one trick. It's really interesting why, if it's like divisible, k divisible by 0 or like k divisible by 5, there is no solution. So it's like obvious because like it's obvious because like the number that ends with ones can be divisible by by 2 can never be divisible by 2, can never be divisible by 5, because it will always end with 1. But why there are no other numbers? Like, why it's not like divisible by 8 or like something like that? That's interesting. That would be interesting to prove. Yeah, but I don't know how to do that right now. But still, that's it.